Hello everyone. In this module we will discuss surface area measurements which are commonly performed on construction materials, for an example cement and SCMs, right, fly ash, slag, silica fume, right. So that will be the topic for this module. So why do we need to care about surface area measurements? The reactivity of a powder is influenced by its surface area or fineness, right. The particle size and specific surface area of a cement powder have a direct influence on its property, hydration kinetics. So as you see in this plot, what you see, there are three different types of, in this case C3S alite tricalcium silicate, right, C3S powder of different particle sizes. So in one case it is around 6 micron, then it is 5 to 13 microns and 2 to 38 microns. So basically we are looking at the effect of the fineness, the 6 micron is the finest one, right. So what you see, it is affecting the hydration kinetics, right, hydration kinetics, right. As you go towards the higher sizes, there is not as much as acceleration you see in the case of the finest powder in terms of particle size, right. So what does it tell you? That the size and surface area have direct influence on hydration kinetics. If it has direct influence, then it will also impact your rheological and mechanical properties, right. Rheological properties like the flow, for an example, right, and mechanical properties, because this hydration kinetics will have a role on that. So these are for different sizes. So size range is around that. These parameters influence the interaction between cement and chemical admixtures such as superplast. We use these admixtures to modify the properties, early age properties in some cases, right. So like rheological properties. So that interaction also is influenced by the size and surface area. Okay. So now it is clear that, we need to understand, or we need to measure the surface area of a powder, for an example. In this case we are talking about cement powder, right. So what are the typical measurements which we do, right? All of you are familiar with these two aspects. One is particle size distribution, right. We want to get an estimate of particle size distribution. What is the size range of particles in a powder, right. Basically the size distribution influences the handling, storage and domain of use of a powder, because that will affect your hydration kinetics in case of cement, right, that we have already seen. Surface area is nothing but total surface area, right. We are talking about the total surface area of powder. Specific surface area is the normalized way of normalized surface area. So we can normalize it by usually it is normalized by the amount. Like if you have two different amounts of powder, right. So one case you have 10 gram of powder, in other case you have a 20 gram of powder. So your surface area of 10 gram will be lower than 20 gram surface area, total surface area if you measure. But we are talking about specific surface area, where we are surface area divided by amount, mass. So we are talking about per gram, 1 gram of powder, how much surface it has, right. It is used to compare two different powders or materials, right. So we are talking about 1 gram of material A has surface area of this, 1 gram of material B has surface area of this, right. So you understand why we are doing this normalization, so that we can use it for comparison. Okay, it typically expressed as centimeter square per gram or meter square per kg, means that 1 gram of particular material has this much square centimeters of area, right. So, if you look at the images like particle size distribution, we were talking about the sizes, right, can vary. You will have a difference in the size, shapes, right. So, see, we can have very irregular size, as you see in the case of GGBFS, the slag, right, ground granulated blast furnace slag, right. It does not look like spherical, right, it has very irregular shape. You see in silica fume, you have some spherical shapes, also you have some agglomeration, right. And fly ash, also you have what we are showing here, you have a spherical primary particles, right, you have spheres, also you have irregular primary particles, right, they look irregular, not spherical. Then you have agglomerates. Here you see agglomerates, and you have aggregates. Okay. So, agglomerates is just we will come back to it. So, you may have a lot of particles together, some are bonded chemically, some are not bonded chemically, right, there are some physical bonds, that is the difference. So, in aggregates you have some chemical bonding, and agglomerates you have only physical bonds like van der Waals bond. So, the attraction is not very strong, that is the only difference. Now, if we have to come up, if we have to define like particle size, consider you have irregular size, how do you do it, right, that is the challenge. We cannot measure like in one direction, then it is changing, right, it is very irregular. So, we define equivalent spherical diameter, ESD, equivalent spherical diameter for non-spherical particles. For sphere it is easy to define diameter, right, we can say okay, this much diameter, the diameter will be characteristic of a sphere. But if you have non-spherical particles, we do define equivalent spherical diameter, right. So, for an example, in case of volume, let us see, suppose it is just to understand what does it mean is like if you have a cube, right, imagine you have a cube of 1 centimeter size, right. So, you have a volume of 1 cubic centimeter. Now, if you are saying can you tell me the diameter of a sphere which will have equal volume, or tell me the diameter of sphere which will have a volume as 1, that is the meaning of equivalent spherical diameter. This is on the volume basis. You can do it on surface area basis also, right, this is the volume basis. So, what you do, you just suppose this is the radius is r, right. So, this is the volume of sphere, right, it has to be equal to 1, right. So, then you can calculate r, and that you can use to calculate diameter is equal to 2r. So, you can say that the sphere of this size, right, will have equal volume as cube, right. So, that is a convenient way of expressing the diameter, right. So, this is on the volume basis. Anyway, we will come back to it, but I am just telling you, you will use often you will encounter this terminology equivalent surface spherical diameter, right. So, yeah, so we can do this normalization based on total number of particles also. So, we are talking about, let us see, commonly used normalization which we use for average particle size. So, one is based on number of particles, right. So, do you define dn for an example, dn is the number length mean diameter, right, summation of di ni over summation of ni. So, where di is average diameter in that interval. So, you have now we are talking about the intervals, right, size intervals. You can divide your whole range in multiple size intervals, and you know that what is the average diameter in that interval, right, and you also know how many what are the ni is the number of particles in that size intervals. So, these are two different way of normalizing things, right. So, dn is normalization based on the total number of particles. So, you can see that di, ni summation over number of size intervals small n, right, divided by total number of particles. And you can also do normalization based on volume, right, normalization based on volume. So, again the formula will be different, you can use this term, right. So, these are two common normalization we do, okay, normalization based on total number of particles and normalization based on total volume of particles. Though two are different, it is very important when you look at PSD, what is the metric. So, it is illustrated here in this graph. What do you see? We are plotting distribution curve, right. On y axis we have a frequency, x axis we have equivalent spherical diameter, right. So, when you plot on number basis, right, number basis you get this distribution, and when you plot on volume basis you get, so the distributions are different. That is why it is very important to pay attention to the basis. Lot of papers will not even mention what kind of basis they have used, but is the difference when you do number basis versus number of particles versus volume of particle, that clearly shows you it is the same data, right. So, we will come back to it, but these are commonly used normalization as far as PSD is concerned, but you have to know what is the normalization you are using, right. If just frequency and equivalent surface diameter is given, it is very hard to tell what is it based on, and both will have different implications. Yeah. So, many powders have aggregates, aggregation is always an issue, right. So, aggregates basically you will have aggregates where we are talking about the chemical bonds between the particles, okay. And also it may have agglomerates. Agglomerates we are talking about physical bonds like weak bonds, van der Waals bond. And we can measure the agglomeration by defining this agglomeration factor, okay. So, it can be defined as ratio of mean volume diameter over average diameter from specific surface area. So, this is just a formula to define the agglomeration, okay. So, if you have a high agglomeration factor, that means you have higher agglomeration, right, extent of agglomeration. We will come back to it anyway. This the dBET is like a average diameter from specific surface area. So, BET is theory we use to determine the surface area. So, we can get, once you know the surface area and the density, we can calculate the diameter, okay. So, this ratio can be used to define agglomeration, the extent of agglomeration, okay. This is important. So, we are talking, so before you do particle size distribution, you have to have a representative sample, very important. So, see, you are interested in, suppose in determining particle size distribution of a bulk or some process stream, we are talking about significant amount, right. You are interested in knowing the particle size distribution in that, right. It could be in tons, that is the idea. But you cannot carry out particle size distribution on that size scale, right. What you have to do? You have to bring it down, right. So, you always take sample out of it. First your sample will be in really significant amount, then it could be in kgs for an example, you have taken sample out of it, right, gross sample. Then gross sample, from gross sample you will have laboratory sample, right. You will take, okay, you will take some sample where you will do some tests. So, it could be in less than kgs, right, you are reducing the size, but at the same time it has to be representative. Then laboratory sample you will have to do multiple tests, different tests. So, you need sample for different types, right. So, finally, your test sample will be in grams, and each test sample may have multiple measurements. Finally, you are talking about in milligrams, so right. So, see, during this sequence we have to make sure the sample is representative, right. If it is not representative, then idea is we want to know the particle size distribution in the bulk or process stream, right. And finally, the measurement is done in milligrams. For an example, this particle size distribution, if you or any other technique you use, right. So, sample size is very small. So, these things you have to keep in mind. So, for that we have to follow some rules of sampling, These are called golden rules of sampling. A powder should always be sampled when in motion. First rule, powder should always be sampled when it is motion. Second rule, several small samples should be taken at different time intervals or at different positions rather than taking one large sample. You understand? Several small samples should be taken at different time intervals or at different positions rather than taking one large sample. So, these are two rules of sampling to avoid the errors. You see here what happens when you just have a heap of a powder, right. You just leave it, you will have, what will happen, the coarse aggregate will tend to come to the bottom, right. So, you already have a segregation here, right. So, that segregation will induce errors. See, there are two types of errors we are talking about. One is because of the material heterogeneity, that we cannot avoid. Like material itself, if it is heterogeneous, it will lead to some errors. But the second type of error we are talking about is because of segregation, which can be prevented. For that, you have to follow proper sampling process. Okay. So, luckily what happens in cement and similar materials such as slags, fly ashes are very fine powders. So, very large number of particles are there in very few grams of materials. So, if you take a few gram of material, can give you a good statistical average. So, that is the benefit. But anyway, it is good to follow these sampling rules. Also, how do we define a representative sample, right? How do you know how much of sample you need to take? So, this is the formula you can use. The minimum sample weight can be calculated using this formula, right, where, so you see Wm is the minimum weight required in grams, okay, depends on sigma square is the variance of the tolerated sample error. What sample error you are talking about? So, sigma square, okay. Rho is the powder density. What is the density of powder? Okay. Wn is the mass fraction of largest size class sample. So, W1 is the mass fraction of the largest size, okay, and D1 is the maximum diameter of the largest size class samples, right, and D2 is the minimum diameter of the largest size sample. So, D1, D2 are the minimum and maximum. So, once you know this, you can use what should be the minimum sample weight for a given variance of the tolerated sample error. For an example, for a typical cement, okay, this is close to 1 gram for 5% tolerated error. If you want 5% tolerated error, so you know the sigma, you know the rho, right, in you know all these quantities because based on your particle size distribution, right. So, you need 1 gram for 5% tolerated error. If you decide to take only 300 milligrams, then your tolerated error will go up to 10%. You see, that is simple example, right. So, it will depend on the material you are working with. You can't just assume that you will use the same amount for different materials. It depends on these factors. We are not going in detail, but this can serve as a guide whenever you do sampling. Okay. So, how do we determine particle size distribution, right? So, for especially for large size, like what we use for an example sand and coarse aggregate, which we use in concrete, we do sieving. Sieving is commonly used technique. So, simple, it is a simple widely used method for classifying powders according to their physical size alone, right. We do not care about chemical makeup, it is just physical, how they, what is the shape and size, right. It covers a wide range of wide particle size range from 37 micron to up to 125 millimeters, right, quite a bit. And we use woven wire sieves for sieving. So, when you are talking about sieving, what is important? Key variables are particle shape, right, presence of very fine particles, initial sieve loading, how much you are putting, right, initial sieve loading, time and method of agitation, how are you performing your sieving, right, is it manual, is it mechanical, what is the way, cohesiveness of the powder. These are the key variables, right, which can affect your sieving results. So, due to the size limitation at the lower end, we see that we cannot go below for an example 30 microns, that becomes really difficult to sieve. So, sieving by itself is not a suitable method for characterizing the complete PSD of cement powders. So, we can use it for coarse materials, but for cement where your particle size ranges from less than micron to hundreds of micron, right, it may not be a suitable method. So, better suited for analyzing large size fraction contained in cement powders, like which are larger than this 50 microns for an example. But also care must be taken while cleaning and handling sieves with apertures below 250 micron for accuracy. What happens when you do sieving? It clogs your sieves. So, if you do not clean your sieves, then your results will get affected. It is very important. You have to pay attention, especially as you are going down the size. Everyone must have seen this. This is a typical sieving apparatus, right? This is the mechanical one. So, you do not have to manually shake, you can mechanically shake it. So, you have different sizes, right, they are stacked on top of each other, right. So, this is a typical particle size distribution, or this you get this is mass on the y axis, what we have, mass or sieving fraction of total sample, like how much of, yeah, in percentage, right, and x axis we have sieve sizes for different types of materials, right, starting from gravel, sand, silt, clay, right. It can tell you like which one is finer, what is the range,